is tough to find the exact functions, so the mathematicians try to find asymptotic behavior of this type of functions, which we call arithmetic functions. Arithmetic functions are functions which take input from natural numbers and give output complex values. So today our topic is about prime number theorem. This is basically this is also the same problem. Here we are trying to find out what is the behavior of phi x, which is the prime counting function. This is number of primes. This is the arithmetic function, and we are here trying to find out what is the asymptotic nature of this function. Okay. Now, many people have tried to solve this problem for many years. The first proof was given by Adamant and Hussein in 1896. The second proof was given by Selberg and Paul Riodos. This does not use complex analysis, but finest proof given in 1980 by Newman, which I will state today. This uses a bit of complex analysis, and we'll do this proof. Before going into the proof, first we need to know some notations which I will be using in this talk. So first is of x. Any function of x. Big O notation, that means that this is equals to some g of x, that implies this is the definition of economic. Here is c comma belongs to 0 such that for all x greater than equals to c, g of x, and say this asymptotic notation, say fx is asymptotic to g of x, that if I only limit x tends to infinity, f of x g of x equals to 1. Now we are introduced to some of the arithmetic functions, and not of the normal arithmetic functions, but different functions too. The first one, you know the pi of x. This is number of primes less than equals to x, and secondly phi of x, which is summation over prime less than equals to x log b. Well, basically you can see that phi of x is this is like the summation over prime less than equals to x 1. So while we are using phi of x, a little bit motivation of this, like phi of x is adding some weight to the primes. But basically the phi of x, here if you plot this with respect to values of x and its values of phi of x, you can see that it is a little bit unsmooth. If we add some weights to the primes, this becomes a little bit smoother. Now I'll introduce you with item z. This is summation over prime log b because z, and finally Zeta of z is summation over equals to 1 to infinity 1 to n power z. This function and a complex value. Here the Z is a complex value. So and this will give output like this. F of 1 by 1 plus 0 plus f of 3 by 2 plus 7, so on. So this is nothing but n equals to 1 to infinity f of n by n power 7. So here you can see that this is well the most general Zeta function. The most general example of this is the Zeta function, which it is written here. Which if you take the arithmetic equal to 1, and the Zeta function is quite related to the distribution of primes. I will talk about this in this proof. And the phi of z, this also comes really naturally from the distribution of from the Zeta function. If you take derivative and some other operations on this, you get see that phi also comes really naturally. I will show this later on this proof. And yeah, all of the in both of these cases, z is the real part of z is greater than 1. For this values, this both of the series will converge. Okay. So now we will head towards the proof. Well, the proof has basically 4 parts. The first one is psi x is asymptotic to x. This implies phi x is asymptotic to x by log x. The second one is assume integral 1 to infinity psi x minus x by x square x is then we will show psi x is asymptotic to x. Here we require a substep which is phi of x equals to b of x. We'll prove this because we will need this in the third step, which is the existence of the integral. Now I will introduce so this is our goal and the main steps to do this. The first 2 parts of this also does not require anything related to complex analysis, but the last part is this will require some complex analysis. So before proving I'll start proving from this why this integral exists implies that psi x is asymptotic to x. Let us assume that integral 1 to infinity psi x minus x exists, and on contrary that it is not on contrary that psi x is not asymptotic to x. Now, what does actually psi x is asymptotic to x means? Psi x is asymptotic to x means that limit x tends to infinity psi x by x this is equals to 1. If I write this in the way of in the way of analysis, this is nothing but all the starting greater than 0, the resistance r greater than 0. So this is for all Now we're saying that if this condition doesn't hold, that means limit extends to infinity size base is not equal to 1. What does that actually mean? That would mean that there is a epsilon greater than 0, such that for all r greater than 0, their existence is greater than equals to r, such that x by x is either greater than 1 plus epsilon or x by x is less than greater than 1 minus epsilon. So now I will restate this statement in a different way. Large x such that phi of x is greater than or equals to lambda x, or for some lambda less than 1 there exists arbitrarily large x such that phi of x is less than or equals to lambda x, and will show that if either of these conditions holds, then the integral cannot exist. Let the first condition is true. Consider for some lambda greater than 1, there exists arbitrary large x is greater than or equals to lambda x. Now consider this integral x to lambda x. So if this integral I can show that this has some finite positive value for any x, then this integral, then the initial integral, this integral does not converge because of the Cauchy's theorem. The psi is an increasing function. This is equals to lambda x minus e by t square dt. This will turn out to be lambda minus 1 minus log lambda, which is always greater than 0 for lambda greater than 1. So this is a fixed positive value, and by Cauchy's theorem, this integral cannot exist. then lambda is less than 1, so we will have to take the integral for lambda equals I plus t minus t by t square dt. If we similarly evaluate this integral this way, you can know that this is less than equals to 1 plus log lambda minus lambda, which is less than 1. And this is a fixed positive value, fixed negative value, and I can choose arbitrary value of x, arbitrary large x here. So this the integral cannot exist. So we have shown that the psi x is not asymptotic to x. This is false. So psi x is asymptotic to x. Now we will go to the proof why this integral exists. And here I will use theorem of complex analysis, which so I will state the theorem that f is a function from r plus Newman subtending 0 to r bound and locally integrable. We can define g of z to the integration of 0 to infinity f of t power minus z dt if g of z exists and holomorphic. I will discuss the terms later. Holomorphic for real part of z than 0, and if there exists a holomorphic extension of g of z, say g into z, then the integral is 0 to infinity f of t dt exists and equals to basically here I will now discuss all of these terms here. This process of taking g of z, this is called Laplace transform. Laplace transform is a process where if you are given a problem of real analysis and you will convert this into a problem of complex analysis. Now I explain what are the terms holomorphic means. Well, holomorphic means complex differentiable. Complex differentiable is nothing but this limit h tends to 0. That is the function. Both of the functions are same. T is a function from is a function on is a complex variable function. E of z plus h minus e of z by h, and here h is a complex value. So if this integral exists, so if this differentiation, if this derivative exists, then we can say then this is called, if it is called complex differentiable, and the value of this at z, this is called the derivative. So basically complex holomorphic means it is holomorphic in the domain of this domain of this function. And what is a holomorphic extension or analytic extension means? Well, analytic extension is like if you are given a complex valued function, say in I'm just giving an example, say mod of z, this is less than 1. You are given a complex valued function, say in this region, and if you want and you are wanting to define this function over a larger region than this. So define the larger region f tilde. This is defined in more less than 2 in this region. And here f is complex differentiable. So f tilde will also be complex differentiable. I'm not showing this how this comes from that. Okay. So this and basically the important thing is analytic extension is unique in complex valued functions. If you are talking about real valued functions, you can extend it many ways. This may not be unique. Right? Like if you are given a function is from -1 to 1, x square, you can extend it like this or like this. You can extend this in infinitely many differential ways such that it is differentiable in larger domain, say all over, say over R. But in complex analysis, all of these functions collapses to only one function. Okay, I'm not showing how this works actually. Just using the fact. So we are using this theorem, I will show why the integral exists. So in this case, we will take f of t, I of t for t minus t for c, e to the power p, and g of z, you get this is infinity. Well, this is here a function from r plus union 0 to r. To the power p minus to the power p by to the power minus ft dt. If you evaluate this value for either part of z greater than 0, we see that this will turn out to be I of x minus x by x to the power z plus 2. So now if you take this term, phi of x by x to the power z plus 2 minus 1 by x to the power z plus 1 dx. This is why we require this part. The phi of x is O of x. Because if you take phi of x is not O of x, let's say phi of x is increasing like x square, then this integral may not converge for real part of z greater than 0. You can visualize this for only real values. This is enough for complex values. So I will give a short proof why this why phi of x is O of x. Well, take this function minus phi of x by 2. This is equals to product. This is equals to, if you expand this over this and the function of the log t is greater than x by 2 less than x. Now if you evaluate this, this will turn out to be product over primes e greater than equals to, so e greater than box of x by 2 less than equals to box x, and this is less than equals to box x plus box of x by 2. Because in this term, all of those primes which are between this would not be cancelled out by take the box of x by 2 factorial. this is less than equals to 2 to the power of x. This is less than equals to 2 to the power of x. Now, if you take log on both sides, then basically by induction you can show easily why phi of x is 2 of x. Now I'll proceed here. If you evaluate this integral will finally turn out. If you now expand this as form of as this definition, summation over log e less than equals to x because x equals to, and this integral is dx, and this will turn out to be 1 by z. And now if you evaluate this, now this is just numerical manipulation. You will find out this term will be equal to 1 by z plus 1 summation over e prime log e by e to the power z plus 1 minus 1 by z, which is nothing but 1 by z plus 1 phi of z plus 1 minus 1 by z. So this is actually with the Laplace transform is acting like a bridge between these arithmetic functions and this L series. Now you can see that very naturally this arithmetic functions and this L series are related. Okay. Now this is enough to find an analytic extension of this function in the region real part of z greater than 0, which are right here. So our final goal is to find an analytic extension of 1 by z phi z minus 1 by z minus 1 in real part of z greater than equals to 1. So this is our final goal. This part, now in this part we'll use little bit of complex analysis. Now give analytic extension of zeta function here. As you seen that zeta function is defined in such a way that it is only defined for the half plane. So this is the real part of z equals to 1 line. So this is defined only in this plane, not including this line. So now I will give some extension of this, which you can see, which will be defined over all of this region, real part of z greater than 0. So basically, the analytic extension is here. I am this zeta and this zeta here are different. This is an analytic extension of this, but I will write. I'll denote these analytic extensions by same notation for simplicity. Now you can see that this integral exists for real part of z greater than 0. So we have defined zeta z such that it is defined over all of this region, but only problem is that z equals to 1. Here z equals to 1, we are taking the pole. Pole means that the function is tending to infinity at that point. And it is a complex differentiable at all of the points except for this only one point z equals to 1. So now I will evaluate why this is equals to the formal definition of zeta s for real part of z greater than 1. For real part of z greater than 1, this will be I will break this integral in parts from n equals to 1 to infinity n to n plus 1. Now, if you then evaluate this, after some steps, you will finally see that this is nothing but the actual definition of theta s here. So, we are part of z greater than 0. Why are we discussing this function? Because here this zeta s for all of in this region real part of z greater than 0. This is the complex. This is also complex differentiable or holomorphic, except for this point at z equals to 1. And complex differentiation. In complex differentiation, you can also for this term you can interchange derivative and integration. You can try to show this for this words here. Now I will relate why I make this analytic extension of zeta function. I made this analytic extension of zeta function because I am going to use to describe describe this function. Well-known thing that zeta of this is product over all primes 1 by 1 to the power z minus 1 for part of greater than 1. This one can show easily using basic definition of convergence. So I am not showing this here. And if you take zeta prime z by zeta z, well, zeta z is equal to summation over log b by 2 to the power z minus 1 over all primes. You can create this like this over all primes. Log b by 2 to the power z plus summation of all b log b by p to the power z into p to the power z minus 1. And this is what we know part of z, and this part say I am denoting as of z. So here in this case you can see that we are trying to find some analytic extension of phi of z in this region, in the region real part of z greater than equals to 1 of this expression, and this expression is defined and holomorphic for z greater than equals to half, because as this primes get larger, p to the power z minus is holomorphic for Z that for real part of Z equals to R. And so yes, we have defined zeta of this in this way, that is, it is defined in real part of zeta greater than 0. So this this expression, say this 1, so 1 is holomorphic everywhere in level of greater than 0 except for use of figures or use of primes. Only in these cases, this yields you some problem. In other cases, this is just fine. So now we'll show that we can define this in a way which is favorable for us. Basically, this includes that zeta of Z does not have any root on real part of Z equals to 1. Therefore, real part of Z greater than 1, as phi of Z is well defined, and if the zeta function have a root for real part of Z greater than 1, phi of Z must have a pole at that point, which is impossible because phi of Z here in this case is for real part of Z greater than 1 is well defined. So only problem arises when real part of Z equals to 1. Only in this case the zeta Z can be 0. I'll show that here also it cannot be 0. Okay, so if some alpha greater than 0, if any alpha let 1 plus minus I alpha is the root of zeta Z of multiplicity mu, because if 1 plus alpha is the root of zeta function, then by symmetry of zeta function, the zeta function must have a root at 1 minus 1 by alpha. You can simply take the complex conjugate here and see this way this goes. Let 1 plus minus 2I alpha root if this holds, then zeta prime Z by zeta Z minus of this if zeta has a root near this, then if you evaluate, if you take okay, so basically if the function is complex differentiable, then you can find something like Taylor series in complex variable near that value. So if you take the Taylor series of zeta function near any root of zeta function and evaluate this term, you will see that near any root this function acts as like mu by minus mu by Okay, so and now if you evaluate phi of 1 plus minus I alpha plus epsilon times epsilon limit exponential real value epsilon tends to 0. This will be like here you can see if I put 1 plus I alpha plus epsilon and then multiply by epsilon, then the limit epsilon tends to 0 as this function, this part is holomorphic and this f of z here this is holomorphic. If we tend epsilon to 0, our final expression would be minus 2. And similarly for minus 2I alpha also. So here we'll evaluate easy expression and show that it cannot have a root at 1 plus I alpha. Consider this expression. R equals to minus 2 plus 2. This expression will turn out to be, if you break all of this, phi's by definition, you will see that this expression is nothing but e prime log e to the power 1 plus epsilon to the power I alpha by 2 e to the power minus I alpha by 2 or to the power 4 for if epsilon is greater than 0. So this expression is this is always greater than equal to 0. Now if you also this if zeta function has a pole at some point of multiplicity minus u, then this in this expression this will turn out to be plus 2. So it is a pole at 1 plus I alpha, then near 1 plus I alpha this is like this. Now evaluate this term as evaluate epsilon times this term and epsilon tends to 0 plus this will be greater than equal to 0 still. And now if you break in this form epsilon times this and take this to epsilon tends to 0 plus, so you will finally find this expression would turn out to be 6 minus 8 mu minus 2 mu equals to 0, greater than equals to 0, and that implies that as mu is the multiplicity of the roots mu and mu, this must be some non-negative value, so mu must be equals to 0 in this case. And as we have taken an arbitrary term alpha, this the zeta function cannot have a root at real part of z equals to 1. So we have finally proved that this does not have any root at this real part of z equals to 1. Then we can say that zeta prime z by zeta z. This can be written as one by z minus 1 plus some holomorphic term z. This function is holomorphic for a real part of z greater than equals to 1. And this is just simple evaluation. If you take the zeta function near 1 and take its Taylor series expansion, evaluate this, you will simply get this near z. And for the other terms, let az be the minus of this. This is still holomorphic. Okay. So if I take some z multiplied here, then this. If you break this, so you will still find that z minus 1 plus some h of z, which is holomorphic for real part of holomorphic for real part of z greater than or equals to 1. And so finally we have evaluated this value, and using this expression of before, that phi of z equals to minus zeta square z by zeta z minus summation b dot 2 dot b to the power z minus 1 to the power z. From this expression, you can see that phi of z by z, this can be written this minus 1 by z minus 1. This also has a holomorphic extension here in the region here part of z greater than equals to 1. And as this is the final goal, so we have shown that the integral exists. So we have shown that phi x has asymptotic values. Now finally we will show why that implies that phi x is asymptotic is by Laplace. For this, I will use the method of partial summations or the other summation. This is an interesting if you have sequence of complex numbers, and let a of x equals to summation of n less than equals to x, a of n, and let f a function defined from r plus to r. So summation over summation over n less than equals to x, a n f of n, this is equals to x f of x minus integral 1 to x a d f dash t. This is really easy to show. If you break this integral in like this, n equals to 1 to box of x minus 1, integral n to n equals 1, a t f dash t plus integral box x to x a t f dash t. Now in this range into n plus 1 it is fixed. So you can take out an here and try to find out and then you will get here f of n plus 1 minus f of n, and evaluate this. You will finally get this expression. So why this is really interesting, because as you can see, this is the discrete version of what we call an integration by parts. Well, here this ax is equivalent to integration from 1 to x a of x is a function of x, a of x. Right? See, if you evaluate, you will see this summation as an integral, and so this is integration by parts. this, I will show why x is asymptotic to x by log x. In this expression, consider a to be 1 if n is prime, 0 otherwise. So, and if of p to be log. So, now you can see that if we evaluate this expression, this is nothing but summation n less than equal to p less than prime less than equals to s log p, because this is an indicator of prime and this gives weight log p to this prime. So, and for to get this would be equals to an ax would be nothing but sum over 1 from n less than equals to x if it is a prime to count 1 and is 0, so this is nothing but pi of x and log x minus integral log x. Now this function pi t here, pi t is d O of x by d O of t by log t. Well, this is true. This is easy to show using this expression, product over all primes p less than equals to 2n. So p of 2n plus n, where vp is vp of the number. So vp of n is such that e to the power vp of n divides n, but e to the power vp of n plus 1 does not. This is the maximal power of p which divides n. So if we evaluate this expression, this is less than equals to 4 to the power 10, and by taking log on both sides, we will see that summation over n is less than equals to 2n log 2 less than equals to log 2 plus 10, which is less than equals to 10 log 4. Now you can evaluate by yourself why the pi t is O of t by log t. Not explicitly given this proof. Now putting this in here, we will see that pi x log x minus integral of the 1 to x over 1 by log t. This would turn out to be x log x minus over 1 to x and then log to b. This integral, if you evaluate, this is over x by log x. So now if you divide x on both sides, this would be I of x by x equals to I of x log x by x minus O of 1 by log x. This is bounded part of 1 by log x. So if you tend to x tends to infinity, we will find it to be a result. And this other Summation is very interesting. If you take a, you can try by yourself what happens if you take a to be 1 and f of t to be 1 by t. This will turn out to be the harmonic function.